Our plan for today's class is to discuss a little bit more complicated examples of applying compound interest and then proceeding to the discussion of finding a rate and term for compound interest. Let's begin. Our first problem for today will be this. Asifa invested some amount for 6 years. For the first 4 years, her investment grew at 3.5% compounded monthly, and for the last 2 years, the investment grew at 4% compounded daily. How much did she invest if at the end of 6 years she had $10,000 in the account? So this is a process where one rate is changed by another rate. So first it is 3.5% compounded monthly, and then the rate became 4% compounded daily. It is helpful for us to draw a diagram for this situation so that we can clearly see what exactly is going on here. So let's draw a timeline, and on this timeline 0 means today. Then our first important time is plus 4 years, right? So the plus 4 years means 4 years from today. And then the next important time is plus 6 years. And 6 years from today is when the investment actually ends. So let's just make sure that we understand that's its time. Okay. So what other stuff we should put here on the timeline? Well, we know that at the end of 6 years, it is $10,000 that is coming. Another important thing to realize is that in the second part of the period, we have 4% compounded daily. And in the first part of the period, we have 3.5% compounded monthly. What we don't know is how much money was invested today. Okay, I'll erase this problem now because basically now we have this problem in condensed form. Let's remind ourselves how our formula for finding future value and present value look like when we talk about compound rate. Future value is present value 1 plus I into the exponent n. Here, present value is the amount invested, I is the rate per period, and n is the total number of periods. Future value, of course, is the future value of your investment after those n periods. Now, present value is future value 1 plus I minus n. So these are the two major formulas that we should operate. Now, in this problem, you see we have two rates, one rate changing to another rate, which means that we cannot use like this type of formula once, because this rate I is going to be changing from one to another. So we have to use a more advanced compounding process here. Well, I don't know the amount invested in this case. So amount invested would be present value. So I don't know this amount invested, right? But what I know is that this amount invested will be first growing at 3.5% compounded monthly. So plus 0.035 divided by 12, 12 times 4, right? So this is the first part of the process. Whatever that present value was, it was invested at 3.5% compounded monthly. That's why you divide by 12 here. And for 4 years at first, right? So that will be all that will be the future value of whatever that amount PV is after 4 years. But then, whatever that amount is, that amount will begin to grow starting from the end of 4 years up to the end of 6 years. So basically, I need to multiply this by another bracket now, which is 1 plus 0.04 divided by 365 times 2, because it is 2 more years, right? So 2 more years times 2. Now, and that should result in 10,000. So once again, it is important to realize that we don't know this amount PV invested. So this amount was invested here, then it grows for the first 4 years at 3.5% compounded monthly. So that happens after 4 years, and whatever that amount became, right? So whatever that amount became at the end of 4 years, that will now basically become our new present value, which will continue to grow at 4% compounded daily for 2 more years. And the result is, of course, $10,000. Now, what we need to do, we need to find present value from here. So maybe it is helpful to calculate this part first, but we can always calculate this. What I will do for now is that all this part, let's just denote it as some letter A. I don't think I need this anymore. So we denote this part, which we of course can calculate by letter A, and then I can write to you what present value will become. It will be $10,000 divided by this A. So now it is time for us to very carefully compute this, and let's do that. My computation of this part A gives me 1.245817,382, and then I have 10,000 here. Now I can just make that division. And I have 8,026.86. 8,026.86 rounded to 2 decimals. So this is how we will go about solving this problem. You cannot use just one formula to solve this problem. In order to solve this problem, you have to understand how compounding works, and in this case, it's basically one compounding situation is changing by another compounding situation, and that's why we basically go from some unknown present value to a future value after the first period, after 4 years, and then we continue compounding using another rate for 2 more years to get this $10,000. Paulina invested $4,000 at 5% compounded quarterly. For 3 years. What simple interest rate would give her the same benefit? So Paulina invested $4,000 at 5% compounded quarterly for 3 years. What simple interest rate would give her the same benefit? Now, future value will be, it is present value, 1 plus I, n, right? So in this case, we know the present value. It is $4,000 invested 5% compounded quarterly, so we divide it by 4 because there are 4 quarters in a year. And then it's 4 times 3 because 4 quarters in a year and there are 3 years. So let's compute that. So it's going to be 4,643.02. 4,643.02. That's how much the future value is. So what is the interest earned? Interest earned is future value minus present value. We have 4,643.02 minus 4,000. And it's of course 643.02. That's interest. Now we can use this interest to calculate what simple interest rate would give her the same benefit, right? So remember, for simple interest rate, it's I equals PRT. Now let me have a little bit more space here. So we know now the interest, which is given by the compound rate. Now I know that interest is 643.02. And at that point, I will be switching to simple interest because the problem is about actually simple interest. What simple interest rate would give her the same benefit? Well, we know that interest is PRT in simple interest calculation. Therefore, 643.02 equals to principal invested, which is 4,000, right, times rate, which is unknown because we need to find it, times time, 3 years. So from here we find rate, which is 643.02 divided by 4,000 times 3. So let's calculate this. 643.02 divided by 4,000. 0.053585. 53585. Well, if rounded, it is going to be 5.36% PA. 5.36% PA. You see, basically what that means, over the course of 3 years, 5% compounded quarterly is the same as 5.36% PA. Now let's check. We can find interest. We go backwards and try to find interest this way. So 4,000 times 0.0536 times 3, right? 6 times 3 times 4,000. So 643.2. Keep in mind that also we did rounding here in the rate. If with ultimate precision, it's not going to be exactly, the interest that we are trying to reach because of that rounding, but that's okay. I already see that our calculation was correct, keeping in mind rounding. Okay, so that's another problem
Our next problem is this. Over the past 2 years and 3 months, Jack earned $425 of interest. How much did Jack invest if the rate is 6% compounded semi-annually?
In this problem, we're not given future value. We're only given interest. Now, we'll start solving, of course, from our major idea, which is future value equals present value 1 plus I. And that's our major idea. And what we know is that future value can be written also as present value plus interest, like that. Okay, now let's plug here everything that we know, and we'll be able to find present value from this later on. Okay, so what is our interest? So we don't know present value still. We'll keep it as present value plus interest, which is 425. So we still don't know the present value here, so we'll leave it as PV plus 0.06 divided by 2. And here, instead of your n, you have 2 times 2 semi-annual periods per year, and you have 2 years plus 3/12 additional fractional year, right? So it's 2 plus 3/12 because it's 3 months. Okay, so now basically we need to find present value from here. Before we do that, let's make a little bit of a simplification. You see, we can compute this part for sure, right? So we can, if we plug it all in our calculator, that part is computable with no problem. And this part will, denote as A. And that A will be considered to be null. Now, let me compute this part first, and based on that, we'll continue solving this problem. Okay, so this A let me write it here. This A will be equal to 1.142266 687. And I will keep it in the memory of my calculator. So basically, how do you keep in the memory? It's STO1. So I'll store in slot 1 in my calculator. And I'll just have to write it like this. As present value times A. Now, we need to find present value. So we need to solve a little bit of do a little bit of algebra here, right? So you can do present value times A minus present value. So you move this present value to this side of the equation, because solving for present value, you want to collect every unknown, all unknowns to, let's say, to the left side. And it will be 425. So this is a known part, it will be staying on the right side. Okay, so from here we will be taking PV out of a bracket, which is A minus 1. Why we can do this? Because if you go backwards, you will see very clearly, right? So if you open up this bracket, which is a distributive law, so present value times A, it's PVA, minus present value times 1, minus PV, right? So we basically take here PV out of that bracket. We factor out PV, and that will be 425. So our last step will be finding present value, which is 425 divided by a minus 1. Remember that we already have this a, and we can carry this computation now. So we have 2,987.35, rounded to 2 decimals. So that's going to be our answer. Now, why don't we check this? In this kind of problem, when we have a lot of calculation happening, it is helpful to make sure everything is right, and we'll check it. So we'll check on this side. So we now know that we are investing 2,987.35, and that investment is happening at 0.06 divided by 2 at semi-annual rate, 2 times 2 plus 3 over 12. Right. Now I know that this is 4.5, so we can compute this, and to simplify this process, it's going to be 4.5. That's because there are 4.5 semi-annual periods here. So let's calculate this to see what our future value will be like. And I'll also do it just to make sure, to check myself, and you guys also should do it, because checking is an important process. Okay, so the future value is going to be 3,412.35. Now, what is interest? Interest is 3,412.35 minus 2,987.35. Okay, so we can see from here that actually it's going to be 425. So it's going to be 425, which makes it clear that we solved this problem correctly. All right, after this review of compound interest, and after solving 3 more or less more complicated problems involving compound interest, we are ready to proceed to the next part, and that part will be finding I and J. So what we want to find now is periodic rate and nominal rate. Well, I'll remind you that future value is equal to present value, 1 plus I into the exponent n. Right? So what we want to learn now is how do we find this I, this periodic rate. And also, to remind you, J is I times M, where M is the number of compounding periods per year. So if we know how to find I, it will be pretty easy to find J, because all you will need to do is to take that periodic rate and multiply by the number of periods per year. Now, in order to basically find that formula which allows us to find this I, let's just review a little bit of high school algebra related to this type of equations. So if I ask you this simple question, x in exponent 2 is equal to 4. How do we find that x? Well, if you look at this right away, you can say that x is equal to 2. Just because you know that's 2 exponent 2 is 4. But now let me make it a little bit more complicated. If I say 5, now we cannot any longer just know it without solving. So we need some technique to really solve this equation. So what technique would be that? Well, remember, this is an equation. In equation, whatever you do to the left side of that equation, you should repeat on the right side to keep that equation balanced. And another thing we always do when we solve equations is that we want to isolate that unknown. We want to make that unknown somehow standing alone. If this equation, just if this equation was something like this, 2 times, or just to make it more aligned with this, x times 2 equals to 5. If it was multiplication, not exponent, this would be very easy, right? You just divide both sides by 2, and then x would be 5 over 2, because 2 divided by 2 is 1. So x would be equal to 5 over 2, which is 2.5. So that would be easy. But we have an exponent, we don't have multiplication. Well, the process will be very similar. We have this exponent 2. So how do we get rid of this exponent 2? We need to take an exponent 1 over 2, right? That will happen on this side, and because we did it on the left side, we must do the same thing on the right side. Okay? So returning to this exponent, so why does it help us to get rid of this exponent 2 here? Because in your algebra course at school, you should have learned that sum number a into exponent x, and then if you take another exponent y of that a to the x, it will be ax times y. Okay, and if you think about it, so x exponent 2, and if I take exponent 1 over 2, what that does, it gives me this type of exponent, 2 over 2, which is 1. So 2 divided by 2 is 1, so it's exponent 1, which is x. So it means take x one time, right? So exponent 1 means take x one time, so x will be left here alone. And that's what we want. That's what we want to achieve. So this equation here means that x equals, because there is no more exponent here, its exponent is actually 1 here, x equals to 5, 1 over 2, which is basically square root of 5. But we always can use our calculator and compute it. So it's 5 into the exponent of 0.5. And it will be 2.236, and so on. Okay, so that's how you normally go about finding this unknown when there is exponent. Now, there is nothing special about 2. If I say, let's say x into some exponent n, whatever that exponent n is, so the same logic will apply. It will be just, I will be finding 1 over n exponent here, which will be so n will be divided by n, so it will give you 1 here, and then you will have 5 over n. Because remember, this n will be any number, so I will be able to calculate it. For example, n can be 4, and then it will be 1 over 4, n can be 365, it will be 1 over 365, and so on. So I'll plug it in my calculator and compute it. So this is just a little bit of a journey back to your school algebra to remind you how we went about this. Now let's look at this, situation, and let's consider first example where we will try to find this I without using any formula, but using this idea that I just talked about. Okay, let's just erase this, and our first problem will be this. So you invested $2,000 for, let's say, 7 years. at a nominal rate. Let's put it all in proper words. Compounded monthly. Okay, so what is that nominal rate? So what is the rate? What is the rate if you had 4,500 at the end of 7 years? So you invested $2,000 for 7 years at a nominal rate, which we don't know which it is, compounded monthly. That's what we know. We know that the rate is compounded rate and it's compounded monthly. So what is the rate if you had 4,500 at the end of 7 years? You are getting 4,500 as your future value, and you know that $2,000 was invested at some rate I, so we don't know that rate I, we'll just keep it as I here. It's a periodic rate. It's a periodic rate per period, which is in this case monthly, so it's a rate per month. And N is 12 times 7, right? 12 times 7, because that's the total number of months that the rate has been compounded. Okay. Well, just to keep it a little bit more clear, you can see that if we already multiply 12 by 7, right? So it will be 84. And I will need to find this I. So how do I find this I? So first of all, let me divide by 2,000. So 4,500. I'll divide by 2,000. It will be 1 plus I, 84. Okay. I will not need to compute this for now. I'll just leave it for later, just to show how things will look like, and so that we can convert it to formula later on. Well, I need this I, right? So, but first I need to find 1 plus I. 1 plus I. And in order to find this 1 plus I will be looking for an exponent which will get rid of this 84. So basically what I'm doing is this 1 plus I, 84, I'll find exponent 1 over 84, and the same I'll do on another side. One over 84. See? So basically I found this 1 over 84 exponent on both sides to get rid of this 84, which means that this 84 divided by 84 will become 1, right? So I don't need this bracket anymore. It will be just 1 plus I equals to this. Well, that means that I equals to this minus 1. Okay, so let me calculate this. It's going to be 1. It's going to be 0.0097. That's a rounded number, because then I have basically a 0 after that. But that's rate per period. I need still to write it maybe in percentage terms. So it's going to be 0.97%. We need to always remember that this I is per month. It's a per period. It's a periodic rate, right? So it's 0.97% per month. It's a rate per that period. But this rate, of course, is compounded monthly. So after each period, then a reinvestment will be happening, and for 84 times, right? Now, from here we can deduct our J, and I'll write it here. J will be 0.97 times 12. 0.97 times 12. So it's going to be 11.64% compounded monthly. Okay, before we proceed, let's check it, because we always need to check it. We also did some rounding. We need to make sure that the effect of that rounding is not that drastic. And let's see. Okay, so we will need to invest $2,000 at 11.64% compounded monthly, so 0.1164 divided by 12. 12 times 7. So how much we're going to get? We're going to get 499.75. Well, how much we should get? 4,500, right? But we're almost there, right? It's 4,499.75. Now, the reason we do not get the full 4,500 is because we rounded our rate. It was not the perfect all decimal rate, so we rounded, and that's why we lost basically 25 cents here. But that's an important information that first of all, you see that the solution was correct, and then you see that then you also learned what kind of effect your rounding had on the future value. Now, let's use this problem, and let's use the solution to this problem basically to analyze how could we simplify these type of solutions for future, and how could we probably find a formula that we could use in future to save time to compute for problems like this. Well, we will do the same thing, right? So future value is present value, 1 plus I n. So from here, I can find that future value divided by present value is going to be 1 plus I exponent n. I will be looking for future value divided by present value. It's going to be exponent 1 over n equals to 1 plus I. And from here, I'll deduct that I is going to be future value divided by present value, 1 over n minus 1. And that's basically the formula that we will be able to use to find I. Well, even in this problem you can see. So you basically could right away take 4,500, put it here. Then instead of present value, you can take $2,000, 1 over total number of periods. So you would find it as 84 minus 1, and right away you would get your I. You should never forget that I is rate per period, so you will have to find J after you found I. Now let's explore the use of this formula maybe on some other problem in which we'll try to use this formula right away.
This problem reads, what nominal rate compounded daily would double an investment in 10 years?
Okay, so in this case, we don't know present value, we don't know future value, We just know only that future value is going to be 2 present values, right? That's what we know. In other words, what that means is that each $1 will become $2. The investment will double. So we can basically use that in our solution. We can take our present value as $1 and our future value as $2, because whatever happens for each dollar of the price will happen for the whole price as well. So let's go ahead and use this idea. Our formula for I is this: future value divided by present value, 1 over n minus 1. Okay, so as we just now agreed, I is, your future value is 2, your present value is 1, so we are going for each dollar of the price. 1 divided by, the rate is compounded daily for 10 years. So the exponent will be 1 over 365 times 10 and minus 1. See? Just to note here, because the exponents are so complicated, right? So when it's basically 3,650, and then you will, and that's your denominator, your calculation will be very sensitive to rounding because of very high exponents here. It is very important that you do not round anything until you reach the final answer, right? So keep the necessary components in the memory of the calculator if necessary, but don't round intermediate calculations. So let me compute this. So this I is 0.000189921. You see, I'm not rounding anything. So the way I did it, I calculated this exponent first, which is 1 over 3,650, and kept it in a memory of a calculator, kept that number in the memory, and then I took 2 into that exponent and minus 1. So that's the result. And that's my periodic rate, which I don't need to convert right now to percent, because in fact the problem is asking for nominal rate. I still need to find J. So how do I find J? J is I times I. J is I times the number of compounded periods per year, which is 365. So whatever that number is, which I received, I will multiply by 365, and it will be 0.0693213. So in terms of my answer, it is going to be 6.93% compounded daily, right? So that's the answer. The nominal rate is 6.93% compounded daily. Again, it is helpful to check the calculation just to make sure, and also to practice with finding future values. It always helps, right? So future value is going to be some amount, which is $1. Let's invest $1. So for each $1, we should get $2 as our future value, but let's see if we get it or not. So it's $1, 1 plus this rate, so which is 0.0693 divided by 365. Exponent is 365 times 10. Again, we will use as many decimals as possible as our calculator allows, and let's compute that. Yeah, so I get 1.999 0.57 and so on. So of course you can see that that's actually 2, right, around. We are pretty exact here. There is of course a little bit of discrepancy, which is due to the fact that even calculator, even though I didn't round any decimals in my calculator, but because of those enormous exponents, even calculator has to round internally in order to calculate. And this internal rounding resulted in some discrepancy. It always will be a little bit of discrepancy, but of course, not only that, I also rounded the final nominal rate, right? So here you see I dropped 213, for example, and that also contributed to the discrepancy. But even if you don't round at all, you will still experience some discrepancy when you check, because even calculator has to round internally. But that discrepancy is negligible. So just keep as many decimals as possible, and then when you give your answer, usually you would round to 2 decimals, but if sometimes problem will say 4 decimals, you will round to 4 decimals and so on. Always look at how the problem is phrased in terms of what rounding the problem requests. In this case, there is no request for any kind of rounding, which by default means that we'll round to 2 decimals. That's what we did. Okay, so now let's consider maybe one more example, just to be very clear with this problem. Okay. Let's take an example about a loan now. Took a loan. So Nadia took a loan of $12,000. After 5 years and 60 days, the balance was $13,000. What was the nominal interest rate? Compounded semi-annually. Compounded semi-annually. Or for short, I'll just write CSA. So Nadia took a loan of $12,000. After 5 years and 60 days, the balance was $13,000. What was the nominal interest rate compounded semi-annually? Okay, in this problem, we'll use the same formula, which is I equals to future value divided by present value, 1 over n minus 1. Okay, so in this problem, let me put values in. So it's going to be future value, which is 13,000, divided by present value, which is 12,000. 1 over n. See, I will actually keep n for now as letter n. Why? Because I'll just compute it separately when I calculate for this problem, because it's a little bit more, more stuff to write in this formula, which will make it overcomplicated. So I'll just separately write here that n is going to be 2, because it's compounded semi-annually, multiplied by the total number of total number of years in this case, but it's 5, and total number of years is 5 plus 60 divided by 365, right? Why? Because it's 5 years in this term, and also there is some part of the year, in this case it's 60 days, so 60 over 365 is that fractional part of the year that you have to put on top of 5 years. That will be the total number of years in this investment. And then you multiply by 2 because the rate is compounded semi-annually. So n will be the total number of semi-annual periods. Now we can compute this n separately, and then we will be plugging it in here, and using all that calculation process with the help of a calculator. Let's see what the answer would be. Okay, so it looks like the answer is 0.0077958. So once again, how I did it? So I found this n in the calculator and kept it in a memory. So then I did 1 over that n and again kept that part in the memory of the calculator. Then I would take 13 divided by 12. You don't need to worry about typing those zeros here because they will cancel out. So 13 over 12, and that would be raised into that exponent, which I already have in the memory of the calculator, -1, and that's what it should be. Now that's my periodic rate. Just to remind ourselves that this periodic rate is rate per half year, rate per 6 month. So now the next part will be finding J, and J is I times M, so which is this I times M, which is 2. So there are 2 semi-annual periods. Times 2. And that is 0.015559196. And again, I will have to take 2 decimals for the percent rate. So J is going to be 1.56%. 1.56% compounded semi-annual. Okay, as always, when we solve problem like this, we want to check our calculation. Let's do that. I can erase all this. So we'll check our calculation, keeping in mind also that we made some rounding, and we want to know that how this rounding also affected our solution. So we we'll find future value, which is 12,000, 1 plus 0.0156 divided by 2. Here 2 times 5 plus 60 over 365. Okay, so again, we have to make that calculation. So it's going to be 13,002.72, rounded to 2 decimals. Okay, so we have here 2 extra dollars appearing. So this is the discrepancy I was talking about. So I'm happy that we got very close to this $13,000, which means that it looks like our calculation of nominal rate was correct, but because of some rounding that we made, and because of the big amounts that are involved, it is noticeable that this rounding actually made a little bit of discrepancy in the future value. Okay, but that's expected discrepancy due to rounding. Okay, so let's proceed now to another topic, which is finding term for the compound interest.